Hey there, Coach Travis here with another problem from calculus. So the problem we've got here is we want to find the absolute maximum of this function on this closed interval. So the idea here is that the extreme value theorem says that a continuous function, this is a continuous function on a closed interval, all right, this is a closed interval, will always have both an absolute maximum and an absolute minimum. So the extreme value theorem says this problem has an answer and we have to find it. So, all right, so the strategy we're going to use is the following. So the idea basically is this, that the absolute minimum and the absolute maximum of a continuous function on a closed domain has to occur at either an endpoint or a critical point. So that's what we're going to do. We're going to find all the endpoints. Then we're going to find all of the critical points. And then we're going to plug all those values into the original function. And whichever number is the biggest will be the absolute maximum. Whichever number is the smallest is the absolute minimum. So it's that is the procedure that you can follow every time to solve a problem such as this one. So, all right, so like we said, we want, well, actually, why don't I leave that up? We have the, I have the function written up here on GeoGebra. Oh, and why don't I write the, here, I'll write the interval here too. The interval we're interested in is from -3 to 5. So, all right, so there's the problem. And now I can leave the step-by-step up here so you can follow along. So, all right, so first thing is I identify all the endpoints. Okay, no problem there. The endpoints are x is equal to -3 and x is equal to 5. All right, now, but then the next thing we need are the critical points. So, okay, so critical points. So these are going to take more work. So the critical points, so if you remember, the critical points are numbers that make the derivative 0 or they make the derivative does not exist. So what I need is I need the derivative. So g prime of x, okay, let's see, g prime of x, it shouldn't be too hard. G prime of x is -4x plus 2. So I want to know, when is this function does not exist and when is this function equal to 0? And well, this is just a straight line. So it always exists. So remember, critical points are where the derivative does not exist or the derivative is 0. And so this always exists. So I don't have to worry about that first one. So basically, I just want this, I need to figure out, well, when is this equal to 0? Because that could happen. So let's see here. This would be equal to 0. That means that 2 is equal to 4x. And that means that x is equal to 1/2. All right, awesome. So we have one critical point, and that critical point is x equals 1/2. So again, where did the critical points come from? The critical points were numbers that made the derivative either 0 or they made the derivative does not exist. And so 1/2 makes the derivative 0. So that's my critical point. Okay, so we've done the hard part, and now it's the easy part. So now what I do is I just plug all of these numbers into the original function. So I'm just going to make a table. Here's x, and here's g of x. And so I'm going to put -3 in, I'm going to put 5 in, and I'm going to put 1/2 in. And so what I'm going to use GeoGebra to do this. So I don't, because I can't do all of these in my, actually I could do a lot of them, maybe I could do a lot of them in my head, but I don't want to make a mistake. And I just wanted to show you that you can use GeoGebra to do this. So yeah, so what I've got here is I've got the function programmed into GeoGebra. And so now I can literally just type g of -3. And it tells me it's 22. Or sorry, -22. All right, so this is -22. And then, whoops, I want, let's get rid of that. And now I'll type in what's g of 5. All right, g of 5 is -38. And okay, let me go ahead and type the other one in. What's g of 1/2? G of 1/2 is 2.5. So, all right, so I'll record that on my table. So g of 5 we said was -38 right here. And g of 1/2 was 2.5. All right, so the strategy said that the largest of those numbers was the absolute maximum. So this guy right here, that's our absolute maximum. And the smallest is the absolute minimum. So that one, there's the absolute minimum. And there we go. So I think we've answered the question. The question was find the absolute maximum value. And yeah, we got it. We said it was 2.5. And that was it. Yeah, and so actually while we're at it, I always like to draw graphs of these things. Because that makes me feel good. I like to visualize all the work I did. All of this work was just abstract, and I like to draw the graph so I can actually see it. And so with GeoGebra, it's really easy to draw the graph. And so let's see. So there it is. Well, let's get rid of that. I can see it all. So there's the graph right there. So we can see that, sure enough, it looks like we have a maximum at about when x is 1/2 and y is about 2.5. Yeah, if I wanted to, I could go ahead and even plot that point. So I'll say, let's plot the point 1/2 and 2.5. And sure enough, you can see, yep, there it is right there at the very peak. So there's my maximum. And then we said the minimum was when x is equal to 5 and y is -38. And if I look at my graph, it looks like the minimum is happening at about, yeah, x is equal to 5 and y is about -38. So it actually, the calculus didn't lie.